Things they've learned.
They're going to go off and screw it up.
They will screw it up. They will screw it up. Okay, let's get started. Let me have your attention, please. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Mr. John Kotek, Deputy Manager of the U.S. DOE Idaho Operations Office in Idaho Falls, Idaho. John received a B.S. in Nuclear Engineering from the University of Illinois in 1989. Right after that, he went to work for DOE, but in 1995, he received an MBA from the University of Maryland, and he continued his employment with DOE until 1998, when he joined the staff at Argonne National Laboratory West, which is in Idaho Falls, Idaho. He was there until 2003. During the year 2002, he was the Seaboard Fellow, which is a special competitive fellowship awarded for 1 year, and the person who gets it can work for any U.S. congressman, senator for the whole year, and John worked for Senator Bingaman from New Mexico. Then he resumed working for DOE or for Argonne West until 2003, and then in 2003 he became the Deputy Director of the DOE Idaho Operations Office. And so his topic today is creating the nation's nuclear energy laboratory. So ladies and gentlemen, please welcome Mr. John Kotek.
Thank you very much. It's good to see everyone here today. As Lee mentioned, I'm going to talk to you a little bit about what we're doing out in Idaho to build what we're calling the nation's nuclear energy laboratory. Now, just a little bit of perspective for you folks. I'm with the DOE organization out there. All right, now I work for the government, and it's our job to manage the contract through which we currently operate the Idaho National Engineering Environmental Lab. It will soon be known as the Idaho National Laboratory. So it's our job to set the expectations to the contractor and then make sure the government's getting what it's paying for. It's the lab's job to actually dig into the technical details and do the research that I'm going to talk to you about. What I want to talk to you about today is what we're doing in DOE, both in terms of the nuclear energy R&D programs in general, and then focus a little bit down onto what we're doing in Idaho. But I also want to talk with you a little bit about why we're doing it, because you folks, I would imagine most of you are pursuing nuclear as a career, and you probably get the same question I do. Why nuclear? I mean, people say, we haven't ordered a new plant in this country in 30 years. We haven't brought one online in nearly a decade. And what is it about today that makes us think that nuclear is going to be important? I know, and I think you folks would agree with me, that we see nuclear technology as very important, not just in the energy field, but in a lot of different fields. But nuclear energy in particular is something that we're going to need more and more of going forward. And I want to talk to you a little bit about that and frankly arm you with some information that you can use when you're out talking to people about nuclear and why you've chosen nuclear as a field and as a profession. Because I think one of the things that we in the nuclear profession haven't done a great job of is communicating to people as to why nuclear is important. All right, why it's a beneficial energy technology, why nuclear technologies are important in general. All right, so I want to leave you with some of that information. When talking about the need for nuclear energy, I think it's important to start with really the broadest possible energy context and look at the global energy demand picture. All right, and for those of you who can't see this, I'm going to leave a hard copy and an electronic copy of this presentation with Dr. Dodds for anyone who's interested in studying some of this in more detail. The chart I have up here in the top right is called Climbing the Energy Ladder. And what that's looking at is energy use per person versus economic output per person in various countries of the world. And what you'll see if you look at that is the U.S. up at the top of the chart. Now, each one of those little dots represents a year, so this is over about a 25-year period. And what you're seeing on that chart is the U.S. we've pretty much leveled out in terms of our energy use per person, even while our economic output has gone up. We're becoming more energy efficient as an economy. You see down there on the lower left, countries like China and India that use maybe 10% of what we do on a per capita basis. Those countries aspire to a standard of living and to a level of economic output a lot more like ours. All right, and so what we expect to see is those countries, people in those countries, significantly increase their energy demand. The charts I've got down the lower part of this graph, you see world population is going to go from somewhere around 6 billion people today to maybe around 9 billion in 50 years. All right, we're also going to see energy demand per person go up about 50% over that same time. And so as a result, we expect to see energy demand that's 2 to 2.5 times what it is today in 50 years. And obviously what we need to do, really as a planet, is we need to find ways to meet that energy demand that don't have catastrophic environmental impacts and that are sustainable. Right? Now, when you think about how we're going to meet that energy demand, I think it's instructive to look at where we get our energy from today. And as you'll see from this chart, about 85% of the energy in the U.S. comes from fossil fuels. The world picture isn't a whole lot different from this. Okay? And if you agree that importing more oil, importing more natural gas, all right, burning more fossil fuels isn't the right answer for a sustainable energy future, then what is? Well, this is your menu. And unless we've got a big breakthrough in something like fusion over the next 20, 30 years, this is going to be what we have to choose from. Okay? And as you'll see, nuclear right now is 8% of our total energy in this country. All right, and nuclear's got its disadvantages. We're all, as nuclear professionals, we're all aware of that. All right, we know spent fuel is an issue, but we also know spent fuel can be safely handled and managed. We know plant safety is an issue. We also know that over the last 25 years, we've seen remarkable improvements in the way commercial nuclear power plants in this country have been managed, and we know that there's more we can do to design in safety features into the plants to make them even safer in the future. So we've got good answers, I think, to the challenges that nuclear poses. Right? Other energy technologies also have challenges. Try to get a new hydro plant sited in this country, for example. Right? I mean, you think getting a new nuclear plant built is going to be difficult. Right? And things like biomass, wind, solar, they all have problems associated with them. So when you present it to people as a menu, and you've got to make a choice, right? Nuclear, in my mind, starts looking pretty good, right? Because we realize that if you don't choose something from this, you're not going to have the energy that everybody's going to demand. Okay? So when you're talking to folks about nuclear and why you think it's the right way to go, all right, looking forward, make sure you talk about it in context, right? Because nuclear, like any energy technology, is easy to attack on its own. But when you start talking about it in the context of the other alternatives, I think nuclear starts looking pretty good. Some of the reasons why nuclear starts looking pretty good, one, of course, is the emissions issue. And this chart up here on the top left is from a study that Pre-EPI did a couple of years back, looking at life cycle carbon emissions from various energy supply alternatives. And you'll see the top 4 cycles on that chart are all fossil fuel cycles. You've got, I think, coal, oil, and then 2 different natural gas cycles on that chart. And looking at it from a carbon emissions per unit of electricity generated standpoint, you've got 30 times or more the emissions associated with those fossil fuels as you do with things like nuclear, and things like solar and wind as well. So when you look at the emissions question and you look at it on a life cycle basis, everything has some emissions associated with it because it takes energy and a lot of it's fossil fuel that goes into pouring concrete, making steel, enriching uranium, what have you. Okay, but nuclear comes out to be very competitive with the other, like what we like to call non-emitting alternatives. The other thing that I like to point out to folks is what shows up in this lower chart here, which is the cost of nuclear power. All right, now, many of you have heard about the statement made about 40 years ago that nuclear would be too cheap to meter. Well, that was not a very well-informed statement, and I'm sure the person who said it wishes they could take it back. But the point, things have actually turned out a lot better than some people on the anti-nuclear side would like to admit. Because nuclear, once you've got a commercial nuclear plant up and running, it's actually the lowest cost source of baseload electricity we've got. It's even cheaper than coal, and it's a whole lot cheaper than natural gas or oil. Now, the problem is commercial nuclear power plants cost a lot and take a long time to build. And that's something we're trying to address, and I'll talk about that in a little bit. Now, these advantages of nuclear have been well recognized. and by a lot of people who worry about energy issues. This is the cover from a report that came out a year and a half ago, I guess, from the directors of 6 of the Department of Energy's national laboratories, including Oak Ridge National Lab right up the road here. All right, and those national lab directors concluded that we really need to see an expansion worldwide in the use of nuclear energy, right, if we're going to have a sustainable energy future, really in the country and on the planet. The President's National Energy Policy Group also recognized the importance of nuclear energy as part of our diverse energy portfolio in this country, and they recommended to the President that he support the expanded use of nuclear energy in the U.S. Now, those recommendations, all right, it then have been made. It then falls on us in DOE to take those recommendations and turn them into programs and into policies and what have you that can support the expanded use of nuclear energy in this country. Now, what we have in DOE right now is a little over a $400 million program in the nuclear energy area. It's not all on research and development. In fact, only about a third of it is. Right? The other 2/3 goes for things like facility operations, infrastructure costs, space power system programs, university programs, including maybe fellowships or scholarships that some of you folks are benefiting from. Right? Those sorts of things. There are some people who will try to tell you that DOE spends way too much money on nuclear energy and not enough money on conservation and renewable energy programs. And just so you have a frame of reference there, the budget for the energy efficiency and renewable energy program in DOE is $1.25 billion. So it's about 3 times what we're spending on nuclear energy R&D. So just so in case somebody brings that up with you, you got a pretty good argument back. Now, when I talk about the nuclear energy R&D programs we have in DOE, I like to talk about them in terms of the chronological impact they're designed to have. All right, and I'll see if I can get my instruction right from Lee. Down here, you'll see we've got this light blue slice that's referring to the 103 commercial nuclear power plants we have in the country right now, producing about 20% of our electricity, which translates into about 8% of our total energy, which is the number you saw earlier. Those plants are licensed to operate by the Nuclear Regulatory Commission for a period of 40 years. And if all of those plants ran to the end of their 40-year operating licenses, none of them were renewed, they'd all be gone by about the year 2030. Well, as I mentioned earlier, the utilities are finding that their commercial plants are very low-cost producers of electricity. They want to keep them around. So what the utilities have done, with a little bit of help from DOE, is pursue a couple of things. One is license renewal, which you've probably all heard of. That's applying to the Nuclear Regulatory Commission for an extra 20 years operating license on your plant. The other thing they're pursuing is something called power uprates, which allows the plants to generate a little bit more electricity, which is great. So that's going to keep the plants around maybe until about 2050. The problem is all that really does is maintain the status quo. You're not going to do a whole lot there to meet the increase in energy demand I talked about earlier just by continuing to run the current plants. So what we need to see is some new build. Okay? And that's out here in this advanced light water reactors. All right? What we have is something called the Nuclear Power 2010 program I'll talk to you about in a little bit, where we're trying to work with industry to get them to build the first couple of new units based on some advanced light water reactor technology. Looking longer term, what we'd like to see happen is we're trying to develop something called Generation 4 reactors. And what we're trying to do with the Generation 4 reactors is we're trying to come up with designs that can be used not just for electricity production, but also for production of other energy products like hydrogen. All right, now that's a little bit longer term, and it's a little bit more relevant to what we in the National Laboratory System, us out in Idaho, folks here in Oak Ridge, and others are doing. I'll talk about that in a little bit. First, just a little bit about the Nuclear 2010 program. I talked about commercial plants costing a lot and taking a long time to build. Now, if you looked at the cost of the commercial plants that we have running today, you'd see that the plants that were completed before the 3 Mile Island accident in 1979, those were usually a few $100 million a unit. Okay? After 3 Mile Island, a few things happened. One was the regulator, the Nuclear Regulatory Commission, stepped in and said, hey, even though you're in the middle of constructing your plant, you need to make some changes to your design. All right, so the companies, the utilities that were building those plants had to go back, stop what they were doing, retrofit their designs. That added a lot of cost, right, to their plants. Another thing that happened was you had a lot more folks concerned about a nuclear plant being built in their area, and a lot of people went off and filed suit, or lawsuits to try and stop the construction of plants. All right. You also had, frankly, some instances just where the plant construction wasn't very well managed by the utilities. Those factors all right, we're all magnified by the fact that, I don't know how many of you remember what the economy was like in the early 80s, but interest rates were, the mid-double digits. So if you're sitting on $1 billion construction loan at 16% interest and you're doing nothing but fighting court battles for 5 years, the price of your plant just went way up, all right, and that's what happened. So plants that were completed after 1979, plants that were supposed to cost $1 billion to build would cost 2, 3, 4, 5 times that, right? And that plants that were supposed to take 5 years to build, some of them took decades, right? So we've got to get beyond that. What we're trying to do in the Nuclear Power 2010 program is demonstrate what the NRC has enacted in a streamlined licensing process, where they've tried to build in some certainty for the utilities, right? Reduce the risk for the utilities. Still give people an opportunity to have public comment and weigh in if they're concerned about the plants, but try and give the utilities a more stable licensing regime to work in. Now, it sounds great on paper, it's never been demonstrated. And so what we in DOE are doing is offering to cost share with the utilities some of those first-of-kind costs that we like to call them, to help walk them through the construction of the first new plants, to demonstrate that it can be done on a predictable schedule and within a reasonable cost. So we've got a few applications. We've got three utility consortia. In fact, TVA was one of them that asked DOE for some money, applied for some funds under this program. The others, one was led by Dominion Energy back in Virginia, and the other was kind of everybody else who's anyone in the nuclear business, Entergy and Exelon and Duke and Southern and a bunch of other companies. And we're in the process right now of evaluating those proposals and figuring out who we're going to give money to. Right? But what we've seen utilities actually raise their hands and say, hey, we're interested in potentially building new plants. We want to work with you folks, which is really, really exciting. It's something 10 years ago, if you said we'd see that sort of interest, no one would have believed you. So things are actually moving in the right direction there, I think. Look at a little longer term, all right, and more into things, again, that we in the labs are interested in, maybe you folks are interested in. It's this Generation 4 program. Now, Generation 4 is a group of 10 countries plus the European Union that have come together to say, we're all interested in using nuclear energy as a way to meet our future energy demand, but boy, these systems are expensive to develop and design and demonstrate, so we want to share the costs. So what the countries have done is they've come together, they formed something called the Generation 4 International Forum, and they're working together right now to figure out, okay, who's going to pay for what in terms of development, design costs, research costs. The group went through a process called a road mapping process where they looked at more than 100 different reactor concepts, and they narrowed the list down to 6 that the countries all agreed, hey, we're interested in making some investment in developing these technologies. So now that the down selection has been made, the countries are figuring out again who's going to do what. Closely tied in with that is something called the Nuclear Hydrogen Initiative. And what we're trying to do there, again, is we're trying to find ways to use nuclear for more than just electricity production. And of course, you all heard a lot from the President's State of the Union address about a year and a half ago where he talked about moving to a hydrogen economy and hydrogen fuel cell powered vehicles. Well, obviously, one of the things you got to do if you're going to move to a hydrogen economy is figure out good ways to make the hydrogen. Now, we make a lot of hydrogen in this country right now. The problem is we make it from something called steam reforming of natural gas, where you basically take some natural gas, you burn it, you use the heat from that to split more natural gas. And, of course, what you get as a result of that is carbon emissions, right? So if we're going to move to clean fuel cell hydrogen-powered vehicles, but we're going to make our hydrogen using burning natural gas, all you've really done is take your emissions from the tailpipe and move them back to the production plant. That doesn't get you very far, right? So one of the things we're looking at is the use of nuclear, because, of course, nuclear is a non-emitting energy source. If you can use that nuclear to split water instead of split natural gas into hydrogen and oxygen, you can make your hydrogen in a clean way. Right? So what we're looking at is we're looking at a couple different types of systems. We're looking at thermochemical processes, all right, which run at high temperatures and are basically closed-loop chemical systems designed to split water into hydrogen and oxygen. We're also looking at high-temperature, temperature-assisted electrolysis processes, where basically you take advantage of the fact that as the temperature of your input water goes up, the energy needed to split it into hydrogen and oxygen goes down. And so those are some of the different concepts we're working on in the nuclear hydrogen area. What you'll see up here is you see a timeline that I've got laid out. These concepts I talked to you about, I mean, some of them sound great. The problem is, you could fit the research apparatus on this table in most cases. And going from a tabletop size to a commercial demonstration scale is obviously going to take several scale-up steps. And so these are some of the steps that we think that we're going to need to go through. And we expect to do a lot of out in Idaho over about the next 10 years. Okay. Now, why are we focused on hydrogen? Here's a little more information you folks can use when talking to folks about why nuclear. Because what I'm really focused on here is why does nuclear make sense for hydrogen? We've talked about the cost issue already. I'll talk to you about this one down here right now. All right. We all know what oil prices have done recently. In fact, I saw yesterday they got back over $47 a barrel. They think they're going to head up over 50 again. Natural gas prices have been doing much the same thing. Now, historically, natural gas prices had stayed sort of in the $2 to $4 million dollars per million BTU range. They're up. I guess the latest spot price I've got here is about $5.25. They've been ranging from $5 to $6 in the last year, and they don't show any signs of going down. Right? Natural gas markets are getting tight as like the oil markets are getting tight. Right? The more we rely on things like oil and natural gas, right, things that we're importing more and more of every day to meet our energy demand, the more vulnerable we are to supply disruptions. Okay? One of the really nice things about nuclear that many of you folks already know is the fact that the price of uranium is actually a very small part of the price of nuclear-generated electricity, less than 5%. Right? And so even if uranium prices were to double overnight, the price of your nuclear-generated energy isn't going to go up significantly. So nuclear is a way where we can help insulate ourselves from price shocks of energy commodities. So nuclear's got some real advantages there. The reason this is important is this chart down here in the lower left. And that came from somebody at the Cleveland Federal Reserve Bank, provided that to us. What that's looking at is those little pink arrows are pointing to periods where we had 10% energy cost shocks. What that means is the overall average price of energy went up more than 10% in a fairly short period of time. Now, as you look at the timing of those, 73, 79, and then the early 90s, of course, those were oil shocks, right? All right, first oil embargo, second oil embargo, and then the Gulf War. Now, of course, you see one out there in 2000 as well. That had oil. You know, we saw some Gulf problems there, so there were oil prices went up there. You also had the California situation. So that wasn't just oil-driven, but as you can see, oil plays a big role in all of these cost shocks. The light blue bars you see on those graph are recessionary periods in this country. And, of course, this chart was prepared in 2000. When they prepared it, they didn't realize that, in fact, in 2000, we were also in a recessionary period. So every one of the four most recent recessions had been preceded directly by one of these 10% energy cost shocks. What it shows you is the relationship between energy price and economic performance in this country. Our economy is predicated on the availability of reliable and inexpensive sources of energy. Right? And as energy prices fluctuate, our economy suffers. Now, that may strike some of you folks as a little bit of an academic argument, but frankly, it's an argument that policymakers pay a lot of attention to because they worry about this sort of thing every day. Wrapping this all up, the Generation 4 work and the nuclear hydrogen work, they come together in a project that we expect to go forward with out in Idaho called the Next Generation Nuclear Plant. Now, what that is something called very high temperature gas reactor technology, which I'm sure some of you folks have heard of. One of the 6 Generation 4 concepts that were selected by that Generation 4 road mapping group. First, a little more about the technology. What we're trying to do is come up with a gas reactor with an outlet temperature 900 degrees C or more. Now, that's a real technological challenge, and there's some real issues associated with that. In the fuels area, in the materials area, energy conversion systems, a lot of work's being done both in Idaho and here at Oak Ridge to try and address those challenges. Okay? And so those are some things, if you're not involved in now, you might want to get involved in the future. Okay? Those higher outlet temperatures, of course, allow you to get higher efficiencies, both higher electricity production efficiencies and higher hydrogen production efficiencies. So that's the reason for the attraction of this technology. But there are some real issues that need to be dealt with. So there's going to be some good work going on there. Where we stand with the project itself is DOE this spring put out something called an expression of interest. And it's a procurement term. What it means is DOE is saying to industry and other interested parties, hey, here's a project we're interested in pursuing. Here's what we're trying to achieve with it. Here's what we think it ought to look like. Here's what we are proposing as a procurement strategy. Folks, tell us what you think. So we get comments back from the industry and from other folks, and now we're going through the process of updating that procurement document and plan to try and get something out later this year so that we can actually get going with this project. What we're trying to tie into is the overall DOE schedule for the hydrogen programs, which, and this is everything we're doing in hydrogen is supposed to fit into this schedule. What we're trying to do is, as the government, we're trying to work over the next 10, 15 years or so to have the lead in the R&D role. All right, and we'll develop technologies to the point where industry can start making commercialization decisions, right, and decide if there's a market out there for the types of technologies we're developing. The idea here is by about the 2017 timeframe, we'd have that next generation nuclear plant project done, and then industry can decide whether they want to start building these things. Okay, so you'll see there's going to be a lot of work going on in these areas over about at least the next 15 years. Other things we have going on in DOE, and particularly with the focus out in Idaho, something called the Advanced Fuel Cycle Initiative. And what we're looking at there is essentially better ways of managing spent nuclear fuel. Now, those of you in nuclear know how difficult it's been to get the first Yucca Mountain built. Right? No one's in a big hurry to go off and have to build another one. And so what we're looking at here are, okay, are there ways that we can recycle fuel that are proliferation resistant, that have decent economic performance, and that would allow us to significantly delay the need to construct a second repository. Now, we're looking at a couple different classes of systems there. We're looking at advanced aqueous systems, which are basically built off the Purex technology that's been used for 50 years or more, and trying to find ways to make that proliferation resistant, right? So you don't extract pure quantities of weapon-usable material. We're also looking at what we call non-aqueous systems, where we're looking at other technologies, something called pyroprocessing, right, that again separates out plutonium along with minor actinides, so you have a less attractive product for somebody who might be interested in diverting weapons-usable materials. We've got a lot of work going on out in Idaho. This is actually DOE's biggest nuclear energy R&D program. We do better than $30 million a year in research on this just out in Idaho. So it's a pretty big effort. Other things we have going on, space power systems programs, right? Something called the radioisotope thermoelectric generator work. What this is, these RTGs, it's that black cylindrical thing you see there. They stand about 4 feet tall. And they're used to provide electricity on deep space probes. So like you saw the pictures came back from the Cassini mission a few months ago out to Saturn. The electricity that we use to take those images and transmit them back to Earth came from these RTGs. Now, these have historically been made at the Mound site in Ohio, which is another DOE site, but that site's being shut down. So a few years ago, DOE decided to take all that equipment and ship it out to Idaho. And it's been set up out there at a place called Argonne National Lab West, where I used to work. We built a new facility to put the stuff in. We're setting it up now, and we've got to get this stuff going pretty quick because we've got to build some of these RTGs to support a mission to Pluto that NASA plans to launch in 2006 or 2007. So a lot of activity going on there, not just in the fabrication of the RTGs, but in the production of the plutonium-238 itself, in something called the Advanced Test Reactor we have out in Idaho, then the separations work and the final manufacture steps. So lots going on out there in that area. Something called the Nuclear Energy Research Initiative, something else we've had going on. This program is really starting to go away. It's been a way to provide research for really seedbed money to get good ideas out of the university and laboratory and other communities to try and keep nuclear energy research and development vibrant. This was a real important program 5 years ago because it was kind of the first new program in a long time in the nuclear energy R&D area. Now that we've been going for about 5 years and we're starting to see some real interest in Generation 4 designs and advanced fuel cycle work, this is starting to go away a little bit, but something you may have heard of, so I wanted to cover it. University programs, show of hands, any of you folks receiving fellowships or scholarships through any of the DOE programs? No? One? All right. Are you on a scholarship?
No.
Young man.
Research support.
Research support. Okay, so something called the NEAR program. All right. What DOE has done, I actually managed this program. That's how I met Dr. Dodds about 10 years ago. This program got started a long time ago, but when I took it over in the mid-'90s, we were getting about $3 million a year for research support. It was basically to buy fuel for schools with university research reactors. And we were real concerned at the time that there weren't going to be enough nuclear-trained professionals to do the types of work I just talked to you. You know, if I'd come here 10 years ago and spoke to a classroom like this, would we have been able to fill these seats? Maybe not. In any event, it's good to see a good crowd today. One of the things I think that has helped get more students into the nuclear energy area, and also to maintain the vitality of some of the nuclear engineering programs is the university support. We're doing fellowships and scholarships, the research grants that were mentioned earlier, and a bunch of other things. In fact, I'll just here's the sort of laundry list of things that are supported through this program. But what we've tried to do again in DOE is ensure that there are enough folks like you coming through the pipeline to do the work that I just talked to you about. Now, a little bit about Idaho. Now, back about 5 years ago, I guess, it was starting to be recognized, even under the last administration, that nuclear energy is important. And of course, the concern, starting with the Kyoto talks in 1995, was climate change. And the more people looked at that issue, the more people realized, hey, we're going to need nuclear if we're going to meet climate change goals, and we're going to have any chance of turning around the growth in emissions worldwide. And so back in, I think this was 1998, the Department of Energy said, we're going to need to renew our focus on nuclear energy research, and we need to name a lead laboratory, all right, for nuclear energy R&D. At the time, it was the Idaho National Engineering and Environmental Lab, INEL, and Oregon National Lab that were named co-lead labs for nuclear energy R&D. All right, but I think it's important to note that that happened under the last administration because it shows you that Republicans and Democrats are both recognizing the importance of nuclear energy. Why Idaho? Right. Obviously, Oak Ridge is one lab out of several that have real strengths in the nuclear energy research area. But the thing that you got to recognize about Idaho actually started as something called the National Reactor Testing Station. All right, started back in 1949. And its purpose, its reason for being was a place to go develop nuclear energy technologies. So we built 52 reactors out there over the years. 3 of them are still running. Innumerable firsts on that site. For, electricity production, materials testing, you name it. We've trained thousands of nuclear Navy reactor operators on that site, just any number of firsts out there. It really is the roots of the site. As a result of that, we've got tools available to us out on that site that don't exist many other places in the world. Things like the Advanced Test Reactor. And what you're seeing here is before the initial criticality of the Advanced Test Reactor. 250 megawatt thermal test reactor, nine test loops, plus a whole bunch of holes in the beryllium reflector that can be used to irradiate all sorts of specimens. All right, largest test reactor in the world, very flexible machine, and something we're doing a lot of research in right now. Most of it's to support the nuclear Navy program, but there's a lot of other things, Generation 4 work, advanced fuel cycle work, a bunch of other things going on in there. Some other things like the fuel conditioning facility, which is a large hot cell facility out there where we're actually dissolving spent nuclear fuel and testing separations technologies under the Advanced Fuel Cycle Initiative project. I won't go through the whole laundry list, but we've got research reactors, hot cells, analytical labs, microscopy labs. I mean, you name it. There's a lot of infrastructure out there that allows Idaho to do nuclear energy R&D that you wouldn't be able to do anywhere else. Also, as a result of the history on that site, there are a lot of capabilities, represented in the personnel that we've got out there. And I won't go through the laundry list, but just about every area that's important in the development of new nuclear energy technologies is represented by the capabilities that exist out there at the laboratory. That's what led the Secretary of Energy to come out 2 years ago and say Idaho's going to be what he called the command center. All right, for the Generation 4 work, the Advanced Fuel Cycle world. It's really what's led up to the formation of the Idaho National Lab. And now just a brief word on that. What we're doing, right now we've got something called, again, the INEEL. All right, it's a little less than $1 billion a year. But more than half of that, half of the work that the laboratory does is cleanup work. And that's not a way to run a national laboratory, to have more than half of its work being what we like to call muck, suck, and truck type of work. All right, it's not a research-focused institution right now. So what we're doing is we're splitting off the cleanup piece from the research piece. The research piece is going to be covered under a separate contract. We're also merging Oregon National Laboratory West, which is where I work, which is about 600 people in Idaho who actually work for Oregon National Lab, which is based outside Chicago. We're folding those folks in. They've also got a strong historical nuclear energy R&D focus. We think what we're creating there in what's going to be called the Idaho National Lab is going to be a very strong nuclear-focused institution. Right? And that's our job in DOE, is to make that happen. Where we stand in making that happen is we put out something called a request for proposals. We've got bids in for 4 different groups that want to run the laboratory. We're going through the evaluation process now. November 15th, we'll pick a new contractor, and February 1st, we'll turn over the laboratory to the new group to come in and run it. So it's pretty exciting times out there right now. Now, I've talked to you a lot about the nuclear energy work we have going on out at the laboratory. I'd be remiss if I didn't spend some time talking about national security-related work, because that's actually a huge part of what goes on at the lab. It's better than $100 million a year in work at Idaho. Just a few examples of things that we have going on out there, just to give you a flavor for it. In the Homeland Security area, something called the Critical Infrastructure Assurance Test Range. This is a good time for me to mention. But I don't know how many of you are familiar with the INEL or might have ever been out there. If you haven't been, it's a 900 square mile, roughly, site out in the Idaho desert west of Idaho Falls. For perspective, I happen to grow up on the East Coast. I like to tell folks it's about the size of Rhode Island. All right, just sort of puts it in perspective. Okay, and on that site we've got 8 or 9 mini sites. It's almost like little towns, because they've all got the infrastructure that you would expect to find in a town. Between roads and transportation systems, communication systems, electrical, fire, water, you name it. And what we're able to do there on the site that you can do hardly anywhere else in the country is isolate parts of that system. We can, for example, take part of the electrical grid, isolate it from the rest of the site, and say, all right, what happens if we mess with this? All right, let's pretend we're somebody who's intent on doing some damage to the United States. Okay, we're going to mess with the electrical grid a little bit. All right, then we can see what happened. How could we detect that? How could we maybe prevent that from happening? All right, that's something that's very valuable for the people in the Homeland Security Department who are worried about things like that. And what they've done is they've sent us $50 million, or plan to send us $50 million over the next 2.5 years to support work in that area. It's a very large growth area, protecting critical infrastructure in this country. I don't know if any of you have that sort of bent to your work or your interest, but it's something to think about. Another area is in the non-proliferation area, detecting fissile materials and cargo containers. Any of you who have ever been to one of the large ports in this country will know just the huge volumes of material that gets shipped in and out every day. And these cargo containers are a great way for somebody who wants to smuggle something into this country to get it in. And so what we're doing is we're trying to develop detectors that can be very efficient and also work very quickly, because with all the commerce that goes through these ports, you got to be able to do this fast or you're going to cause a bottleneck, and that's going to damage our economy. So we're working on ways to do that. I'll talk to you a little bit more in a second about this change detection system, something won the Lab and R&D 100 award last year. And then finally, the unmanned aerial vehicle area. It's kind of strange. This photo down the lower left, I always accuse these folks of being a front for a model airplane club, but it's not. It's actually real work that's going on. They're developing control systems to control the flights of multiple UAVs over one battlefield or other area of interest. As the military goes more to what they're calling their future combat systems, they're trying to get away from putting people in harm's way and instead putting machines like this in harm's way to do surveillance or what have you. The problem they've been having is they haven't been able to control the flights of multiple units at once, but we're doing that out there. We're developing software systems that can do that, bringing in a lot of new work for us. I mentioned this change detection system a minute ago. This is something that was developed by our intelligence people, looking at ways of comparing seemingly identical images to try and highlight very small changes. All right, so I'll show you this. You've got two shots of a gravel walkway here outside one of our buildings. But I don't know if you'll be able to see this, but as I toggle through the images, can you tell me what's changed? I mean, aside from the angle's a little bit off, but what else do you see? Anyone? The gravel? Yeah, somebody's walked through there, right? And I don't know about you, I'd never been able to pick that up, all right, if I looked at these two.
It was yellow concrete, so one of them are good.
Yeah, and that very well could be too. The thing we're using this for, I mean, it's cute, all right? So you can see somebody walk through this. But think about the applications in things like medical imaging, all right, and taking two seemingly identical brain scans or something. In fact, the guy who developed this technology got interested in it because he saw the difficulty his doctor was having comparing his brain scans. He actually had a brain tumor. Right? He's in remission now, but he developed this as a tool for people to be able to compare images and see tumor growth, for example. So it's got other applications. Like these. We send a lot of people overseas to do work in the former Soviet Union, for example, to help secure nuclear materials that we don't want to go fall into the wrong hands. Well, those people go out, they take their laptops with them, and they leave them in their hotel room, and they go out for the day, and they come back. And well, hotel security in some of these former Soviet Union countries isn't exactly what we'd like to think it is here in the U.S. And they're worried about people hacking into their computers. And so these little spring-loaded keys, they don't pop back to the same place every time. So we've given this tool to our people. They can take a before and after shot of their keyboard, and they can tell if somebody's been in their room while they were gone trying to hack into their system. So we know to look and make sure nobody's planted a virus or some sort of monitoring software on their computer while they were out. So some kind of interesting stuff going on. Just a few examples. Now, I know you live here in beautiful eastern Tennessee. All right, couldn't get any better than this. But, all right, if you're ever interested in coming out, Idaho's got a lot to offer too, especially if you're an outdoors person. Pardon the shameless pitch, but I don't know. In any event, it's a different experience. I grew up in Boston. I live in Idaho now. It's different, but it's great. I encourage you, if you might potentially be interested, and I heard some folks talking about potatoes earlier too. It's very good for growing potatoes. If you're interested in potentially coming out and seeing what we're doing and participating in some of our research, there's a few good ways to do that. One is we've got summer internship and fellowship programs where we bring folks out for 10 weeks in the summertime, pay them a little bit to work with one of the principal investigators in the lab, and just get some hands-on experience working side by side with one of our PIs. All right, good way to come out and see, hey, it's the place for you. All right, we've got some other things. We've got some postdoc programs and some other things. Contact information here for these individuals. Because we're merging INEL and Argonne West right now, there are going to be some hiccups associated with getting the website up, getting the programs in place, but we're working through all that. The summer internship program, the application period usually opens on the 15th of October, thereabouts, and closes the end of January. So within the next month, we expect to have all that stuff worked out and have some brochures out to you folks. I've left some copies of these. This is from last year's program, but it gives you an idea of what the program's about. It gives you some contact information. Some of the details will change, but we'll get you new ones when they're ready. But the idea, again, is if you're potentially interested in working on some of the things I've talked to you about today, come give it a shot. All right? And also, if you're interested in learning more about the programs I just talked to you about, you can start by going to the nuclear.gov website, where you'll find more information on each of these programs and some other things that the Nuclear Energy Office is up to. Okay? So that's what I wanted to share with you folks today, and more than happy to take any questions you've got.
Okay, we have time for questions and comments.
Where is the DOE office located?
In Idaho Falls. In the town, right.
Okay, as most of you know, we do this the webcast. You can ask questions from cyberspace, and we do occasionally get questions.
Okay, very good.
For really important speakers, we get more than one question. So,
oh, well, I should probably just leave now.
We do have two questions from cyberspace.
Oh, all right.
One is from China, and this is a student at Tsinghua University. It's a student that I know, and one of our students knows this student too. The student's name is Fan Li from Tsinghua University in Beijing, China. The question is, we know the pebble bed modular reactor is a promising technology which could become cost competitive, is meltdown proof, and so on. At Tsinghua University, they have a pebble bed reactor, a 10 megawatt research reactor. It's the world's only operating pebble bed reactor. I visited that reactor about 5 months ago. It is said the U.S. intends to build one in Idaho. How do you think the role of the future Idaho National Lab will be with that possible project? And is there a chance, this is his real question, is there a chance for Tsinghua University to collaborate with the Idaho National Laboratory in developing this important technology?
Great, good question. First on the project itself, the thing you've heard about related to Idaho and a gas reactor is the next generation nuclear plant that I talked to you about. And it's still up in the air right now as to whether that would be a pebble bed reactor or whether they'd go with the prismatic fuel, which is something that's also been used. So can't say right now what that'll turn out to be. The idea would be, again, to build a commercial demonstration-sized unit. One thing I didn't mention to you earlier is that we're looking for a 50-50 cost share with the nuclear industry in developing that technology. And so the industry, of course, is going to be interested in demonstrating a technology that they could then take to market. So it would be significantly larger than what they've got over in China right now. nominally 600 megawatts thermal, although that's not nailed down yet either. As for the potential for collaboration, I know there have been some recent discussions trying to open up avenues for more work between the U.S. and China. I can't say specifically where that stands right now because it's something the policy folks back in Washington tend to take care of. But I know that we're looking at potentially collaborating with a lot of countries, the French, the Japanese, the South Africans, others who have interest in gas reactor technology. And my view is the more the better. So we'll hope that develops.
Questions from the audience?
Yes, sir.
Do you think this has a chance that breeder initiatives will be started back up to deal with the waste fuel problem, or then still politically charged that not much of a chance?
That's interesting because 3 or 4, depending on how you look at them, of the 6 Generation 4 concepts are fast spectrum reactors. Now, the original motivation for the breeder reactor was, of course, concerns about uranium supply, and those haven't really materialized in large part because we haven't built as many reactors as we're projecting. All right, when those concerns first cropped up, as a waste management strategy, a lot of what we're looking at in the Advanced Fuel Cycle Initiative would require the use of a fast spectrum reactor to really do the whole job. Okay, I mean, you can do, as you know, you can do mixed oxide fuel burning in light water reactors and get rid of some of your plutonium, but some of the minor actinides and what have you, you really need a fast spectrum to take care of well. So they're still very much on the table, and in people's thoughts in terms of ways to deal with waste. The focus in the near term has been on the thermal reactors, the very high temperature gas reactor, because we recognize we're going to need to, we get a power demand we're going to have to meet. Frankly, because of resource constraints as much as anything, the fast reactors have been pushed off a little bit, but it's still DOE's hope that in the sort of 2020 to 2030 time frame you could see us building some sort of a demonstration fast reactor. And I think the primary purpose would be for waste management first. Obviously, there could very well come a point where we need to take advantage of the breeding capabilities as well, but I think that's even farther down the road.
Any other questions before I go to the second question? I will give you time to think. This question comes from Turkey, and one from China and one from Turkey.
Fantastic.
And in fact, this particular person is a former PhD student of mine.
Oh, wow.
So,
okay.
When do you, and the name of the student, by the way, is Benin Başlo. Some of you will probably remember who Benin, I think he works for the Turkish Nuclear Safety Commission.
Oh, okay.
When do you think a new commercial nuclear power plant will be ordered in the U.S.? And could it be Generation 3 or Generation 4?
First of all, it would certainly be Generation 3. As you may know, back in the, are you folks familiar with the generation terminology when we talk about nuclear plants? When folks talk about, in fact, it was on one of my slides earlier, Generation 1 was kind of the early prototype plants. All right? Generation 2 is really what we've got here in the U.S., plants that were built 60s and 70s technology. Generation 3 is considered the advanced light water reactor plants that were developed in the late 80s and into the 1990s in a cooperative program between DOE and the industry. Through that program, 3 of these Generation 3 designs have been certified by the Nuclear Regulatory Commission for construction, but none of them has been ordered here in the U.S. The industry continues to try and refine those designs, make them more economically competitive. In fact, I think the Westinghouse was first out of the chute. They had something called the AP600, which has been certified. They've got something called the AP1000, which is, I think, getting very close to certification by the NRC, which is supposed to be a more efficient design. A design like that or one of the other Generation 3 designs is what I expect we would see ordered. And I'm pretty optimistic we'll see an order in the next 5 years or so. The Nuclear Power 2010 program of a Generation 3 plant. I think the Nuclear Power 2010 program is helping. If you haven't seen it yet, the University of Chicago just released a study, I think last week, looking at the economic competitiveness of nuclear versus coal and natural gas, and found that nuclear is, in fact, very competitive with those technologies. If you haven't seen that yet, I encourage you to get on the web and look it up. because I think it's a useful thing, a useful study by an independent and fairly tough group of economics folks. The University of Chicago's known to be pretty hard-nosed when it comes to economic analysis. So check that out. But so I do think that in the next 5 years or so, that the timing's going to be about right to see a new order. Although I will preface or caveat my remarks by saying I'm also a diehard Red Sox fan, and this is the year they're going to win the World Series.
All right. Do we have other questions or comments from the audience? Okay. Let me say that. We do have a few new people in the audience, and you don't know that we have a reception immediately following the presentation today downstairs on the second floor, and everyone's invited. John will be down there, and you have another opportunity to talk to him one-on-one and ask more questions. But before we adjourn, let's express our appreciation again to John Kotek. Appreciate it. Great. Thanks.
Oh, and I do have some handouts. Anyone who's interested in that, the summer program or some other things, just pick them up as you head out. That's great. I didn't know you did international. Well, it's pretty fucking bad.